In this video, we derive the equations of motion for harmonic oscillations. As an example, we consider a sphere oscillating on a vertically suspended spring. As explained in the introductory video on oscillations, an oscillation arises from a restoring force that counteracts the displacement of the body from its equilibrium position. If the restoring force is proportional to the displacement, as is the case here, the resulting oscillation can be described by a sine function. Such sinusoidal oscillations are referred to as harmonic oscillations. The sinusoidal oscillation about the equilibrium position can be illustrated by considering a rotating disk with a sphere attached to it. The axis of rotation of the disk is positioned at the equilibrium level of the spring mass system. The distance between the axis of rotation and the sphere corresponds exactly to the amplitude of the spring oscillation. The rotational speed of the disk is then adjusted so that the sphere on the disk reaches its lowest point at the same time as the spring mass system reaches its lowest turning point. If the spring mass system and the rotating disk are illuminated from the side and the motion of both spheres is projected onto a sheet of paper, one observes that their shadows move in perfect synchrony. Thus, harmonic oscillation can be described as the projection of a circular motion. With the aid of this circular motion, the equations of motion of the harmonic oscillation will now be derived. For this purpose, the projected radius of the path must be described as a function of time. We begin by describing the motion starting from the equilibrium position. That means, at time t equals 0, the sphere is assumed to be exactly at equilibrium. At an arbitrary later time t, the disk, and thus the sphere, has moved on by a certain angle phi. This angle phi is not expressed in degrees, but in radians. Radians are generally used for the description of harmonic oscillations. The path traced by the sphere when moving through the angle phi is a circular trajectory with radius r. Since this radius of the circular path corresponds to the amplitude of the spring oscillation, we denote the radius in the following as s max. The displacement corresponds to the vertical component of this distance s max. This displacement can be determined using the angle phi as shown. However, the angle phi is not a constant quantity but changes with time. We therefore need to determine how exactly the angle phi varies with time. This can be obtained from the angular velocity omega of the disk. The angular velocity, as indicated, is related to the rotational frequency f of the disk. Since the angular velocity specifies the angle traversed within a given time, the angular position phi at any time results from the product of the angular velocity and time. If this relation is substituted into the formula for displacement, one obtains the stated equation of motion, which allows the projection of the rotating sphere, and thus the harmonic oscillation of the spring mass system, to be described as a function of time. We therefore see that the time-dependent displacement of the oscillating spring system is a sinusoidal function of time. Upon closer examination, it can also be observed that the sphere moves with relatively high velocity at the equilibrium position, while the velocity becomes 0 at the turning points. This raises the question of how the velocity of the oscillating sphere can be determined. For this purpose, we take a closer look at the sinusoidal course of the displacement. In such a time displacement diagram, the slope corresponds to the velocity. At time t equals 0, when the sphere passes through the equilibrium position, the displacement changes very strongly within a short time interval, and the velocity is correspondingly high. The sphere is then decelerated and reaches the upper turning point 1/4 of a period later. At this point, the slope of the displacement curve is 0 and the sphere has come to rest. The sphere is then accelerated again in the opposite direction and passes through the equilibrium position 1/4 of a period later, this time from top to bottom. The maximum velocity is now negative. The sphere then decelerates again and comes to rest at the lower turning point. After that, it accelerates once more and passes through the equilibrium position upward with maximum velocity. The exact course of the velocity must therefore be determined from the slope of the displacement function. Mathematically, the slope of a curve is obtained by differentiating the corresponding function. In this case, we therefore only need to differentiate the displacement function with respect to time in order to obtain the velocity function. For this, we apply the chain rule as a product of the outer and inner derivatives. Differentiating the sine function as the outer function yields a cosine function. Differentiating the product of angular velocity and time as the inner function yields the angular velocity omega. In this way, we obtain the stated cosine function with which the velocity of the sphere can be described as a function of time. The product in front of the cosine function, consisting of angular velocity and maximum displacement, ultimately corresponds to the amplitude of the velocity and thus to the maximum velocity. We can therefore express the time dependence of the velocity as indicated. Thus, while the displacement oscillates sinusoidally, the velocity follows a cosine curve, which is simply phase shifted by 90 degrees relative to the sine function. We now also see mathematically that the velocity is zero at the turning points, while it reaches its maximum value at the equilibrium position. Note that the term equilibrium position does not refer to velocity, but rather to the restoring force acting on the sphere. In the equilibrium position, no net force acts, which means that this is the balance point where the sphere will eventually come to rest. This is what is meant by the term equilibrium position. During oscillation, however, the velocity is maximal at the equilibrium position. This raises the question of how the force acting on the sphere, which causes the corresponding changes in velocity, can be determined. For this purpose, the acceleration of the sphere must be considered, since according to the fundamental law of mechanics, force is determined as the product of mass and acceleration. The acceleration can be obtained from the time dependence of the velocity. In such a time-velocity diagram, the slope of the curve corresponds to the acceleration. In this case, we therefore only need to differentiate the velocity function with respect to time in order to obtain the acceleration function. For this, we apply the chain rule. Differentiating the cosine function as the outer function yields a negative sine function. The inner function forms the argument of the cosine function as the product of angular velocity and time. Differentiating this argument again yields the angular velocity omega. In this way, we obtain the stated sine function with which the acceleration of the sphere can be described as a function of time. The product in front of the sine function, consisting of angular velocity and maximum velocity, corresponds to the amplitude of the acceleration and thus represents the maximum acceleration. We can therefore express the time dependence of the acceleration as indicated. If at this point we replace the maximum velocity with the product of angular velocity and maximum displacement, the maximum acceleration can also be determined as shown. In order to finally obtain the force acting on the sphere, according to the fundamental law of mechanics, one only needs to multiply the acceleration by the mass of the sphere. The same applies analogously to the maximum force, which can be determined from the maximum acceleration as indicated. This force corresponds to the restoring force that continuously drives the sphere back toward the equilibrium position against its displacement and thus gives rise to the oscillation. The fact that the restoring force, or equivalently the acceleration, always acts opposite to the displacement can be seen directly from the respective functions. From the negative sign in the acceleration function, one recognizes that it is simply the vertical reflection of the displacement function. Thus, displacement and acceleration, or force, are always directed oppositely. The following points should be noted which may at first appear somewhat confusing. Although the velocity is zero at the turning points, the acceleration is maximal there due to the maximum restoring force. When the sphere passes through the equilibrium position, the situation is exactly the opposite. Put simply, the spring is relaxed at this point, and therefore both the restoring force and the acceleration are zero, even though the velocity is maximal there. At this point, the relationship between oscillatory motion and circular motion shall be established once again. We will see that a harmonic oscillation is more than just the projection of the radius of a circular motion. For this purpose, we again denote the radius distance between the axis of rotation and the rotating sphere as r. The resulting formulas for velocity and acceleration are already known from rotational motion. There, the product of angular velocity and radius represents the tangential velocity of the rotating sphere. The product of the squared angular velocity and the radius corresponds to the centripetal acceleration directed toward the center. Compared to the radius, the tangential velocity is phase shifted by 90 degrees, so that the projection of the velocity vector has a cosine-shaped course. The centripetal acceleration is directed opposite to the radius vector and therefore has a negative sine-shaped course when its projection is considered. This is ultimately expressed in the derived equations of motion. We can therefore conclude the following. Not only the projection of the radius, but also the projection of the tangential velocity and the projection of the centripetal acceleration of uniform circular motion corresponds to the motion of a harmonic oscillation. Or, more generally stated, harmonic oscillation can be described by the projection of the vectors of a circular motion. The equations of motion that are derived so far describe the motion starting at time t equals 0, when the pendulum mass passes upward through the equilibrium position. However, we can also describe the motion starting at any other initial time. This can be achieved by introducing an initial angle phi 0 into the argument of the trigonometric functions. The angle phi 0 thus represents the initial position of the pendulum mass at time t equals 0. For example, if we wish to describe the motion of the pendulum mass starting from the moment when the pendulum reaches the upper turning point, the initial angle is 90 degrees. Note that we must express this angle in radians within the functions. The initial angle phi 0 is therefore equal to pi over 2. In this case, we could simply use the cosine function instead of the sine function, or vice versa, and omit the initial angle. However, note that the derivative of the cosine function is a negative sine function, which means that the velocity function now also carries a negative sign. In fact, oscillations are very often described starting from the maximally displaced position, and in such cases, these particular equations of motion are frequently used. Based on the projected circular motion, we have seen that it is synchronized with the oscillation of the spring mass system when the angular velocity of the rotating disk is set to a specific value. How to determine this angular velocity to achieve a synchronous motion and thus mathematically describe the oscillation unambiguously will be shown in a separate video on spring oscillations. We will also see that as an equation of motion, only a cosine or sine function correctly describes the harmonic oscillation. Although we inferred this from the projected circular motion, since it runs synchronously with the oscillatory motion, we cannot be completely certain at this stage. This becomes clear when comparing the cosine-shaped displacement curve with a parabolic curve, shown as a black dashed line in the diagram. Visually, there are hardly any differences, so purely from observing the displacement, a parabolic curve could also have described the oscillation. Therefore, in the video on spring oscillations, it will be shown using a so-called differential equation that only a cosine or sine function is suitable as the equation of motion.